For the last two examples, we are not on the unit circle, right? We can still use sine, cosine, and tangent because those are the ratios of two sides on a triangle, and that's what we're talking about here. Example 11, use an inverse trig function to express theta in terms of x. So when you see that, theta in terms of x, you want theta by itself, and then in terms of means you have your equal sign, and then you have all kinds of whatever on the right side, that's your equation, and you have x as your input there. So we're not solving for x. We're just setting up an equation that uses x as the input and theta as the output. So here's my reference angle, so labeling the sides, there's the adjacent and opposite legs, and that's what we're using. So it's the tangent ratio, right? So tangent of theta equals the opposite over the adjacent, but we're not done because we want theta to be by itself. So when we move the tangent to the other side, we show this by taking the inverse tangent of both sides. Again, we're not on the unit circle here, so the tangent and the inverse tangent will undo each other. So theta equals inverse tangent of that ratio of two sides. So that's what we mean by theta in terms of x. There's the theta in terms of, and x is your input. So now let's do that with all three trig functions. We're going to find the length of the third side, here in example 12, in terms of x, and then we'll find theta in terms of x for all three inverse trig functions. So again, this is the reference angle, so here's the adjacent leg, opposite leg, and hypotenuse. So we start with the Pythagorean Theorem, because we want to know what is the base of this triangle. So a squared plus b squared equals c squared. So a squared plus x squared equals 3 squared. We want to solve for a, and when we take the square root of both sides, we have a, the base of the triangle, which is in terms of x. So again, notice we're not actually solving for x. We're just using this as a way to express the length of the base in terms of x. Now that's it. So we throw out the a, and we're going to use the root 9 minus x squared. You might be thinking, can't we take the square root of 9? Can't we simplify this? And the answer is no, you cannot. Because the rule is, if you are multiplying, then you can take the square root of each individual factor. That simplifies. But if you are adding or subtracting, you cannot, because those are not factors. In other words, you're done. That's as far as you can go. So that can't be simplified. All right, so be careful. Don't try to simplify where you're not allowed to. So that's step one. Now we can find theta in terms of x for all three sides. All right, let's start with sine. Sine is opposite over hypotenuse. So theta is inverse sine of those two sides in ratio. So opposite over hypotenuse. What about cosine? Theta is the inverse cosine of adjacent over hypotenuse. And lastly, theta can be represented as this ratio, the inverse tangent of opposite over adjacent. Now again, another weird item comes up right here. We have always rationalized the denominator, but we're not doing that this time. And I'm just keeping consistent with what the book does. The book does not in this section, and I think it's because they want to clearly communicate which two sides of the triangle we're using and what the ratio is. So we can clearly see, this is the opposite side, this is the adjacent side, and we're not doing anything else. So we're just going to keep it like that, and we're done.